This week, we're looking more at discriminant analysis, and so we're going to start with quadratic discriminant analysis. So one of the assumptions of linear discriminant analysis is that the covariances for each group are, or the population covariances for each group are equal. When this is not true, we can use quadratic discriminant analysis as an alternative to linear discriminant analysis. I didn't write out all the math. It's pretty complicated. It's in the book. I put the page number of the book up here. I'm just really going to show you how to do this in R because the practical upshot is that it's very similar to just regular linear discriminant analysis. So in practice, the assumption of equal covariances really almost never technically holds. It's almost never going to be true that the two group covariance matrices are going to be exactly the same in the population. But it's an impractical assumption to reject unless we have a sufficient sample to really reliably estimate the population covariances. So in general, you're going to want to look to the quadratic method in cases where you have a really big sample, or in cases when the differences in the population covariance matrices are known or can be assumed to be fairly large. If there's small differences, then linear discriminant analysis is going to be fine. So linear discriminant analysis is probably what you're going to use more often. Especially if you have a fairly small finite sample, and then also in cases where the differences in the population covariance matrices can kind of are either not known or you can't really assume that they're going to be super large. The other reason we like linear discriminant analysis is that it has a direct relationship to MANOVA that quadratic discriminant analysis does not, and we're going to talk more about that in later slides today. But first, let's just quickly go over quadratic discriminant analysis. So this is the same as the example from last week. We're using the same mean vectors for people who either have COVID or do not have COVID for temperature and oxygen levels. But the difference is we're going to use different covariance matrices for our simulation here. So the simulated parameters for people who are sick have slightly larger variances and are more highly correlated, whereas for people who are healthy, the variances in both variables are smaller and they are less correlated. So this is the same structure as the data file we were looking at last week, and this is called the quadratic COVID. And so just remember again, this is hypothetical simulated data. Don't treat it as real. So one thing we might want to check is the box M test to see if we can, if we need to reject the null hypothesis of equal covariance matrices. So here in this case, I run the box M test. I get a large chi-square, a p-value below 0.05. So I reject the null hypothesis that the covariances are equal. And so when this is the case, we at least want to think about this quadratic discrimination. We don't necessarily want to default to it. Because remember, this test is very sensitive and it can be rejected even in cases where it doesn't really, it's not that, it's okay to keep the assumption of equal covariances, even if the test says that they're likely not equal. But if you're rejecting it, this is at least evidence that you should consider quadratic discriminant analysis. So here we just, this would be the results for linear quadratic, linear discriminant analysis. So we're just using the LDA function like we used last week. And so the only difference for quadratic is that we use QDA instead of LDA. And so we can see the results here are quite similar. They're a little bit different. So we only make 29 errors for quadratic and we make 30 for linear here. And so we do see that they produce slightly different results and that the quadratic function is actually minimizing, is making slightly fewer errors here, at least based on the data that it was fit on. But of course, we would prefer to do things using the leave one out cross-validation method. So let's just do that moving forward. And so here we see we actually wind up making the same number of errors for quadratic and for linear, though the distribution is a little bit different. So we're making 23 false negatives and 17 false positives here for linear, and we're making 24 false negatives and 16 false positives for the quadratic. So here are the plots. This is the linear plot. You'll see they're gonna be almost exactly the same. There's just gonna be two observations that are gonna flip. I think this like red one down here is one of them. And then there's another one up here. They're both gonna be pretty close to the separating line. So yeah, so this red circle changes to a blue X. And where's the other one? It's this, this red X becomes a blue circle in the quadratic plot. So those are the classification differences. You can see these are both borderline cases because they're both right in the middle in terms of classification. So since they have the same number of correct classifications, I should say correct classifications, not just classifications, what does that mean about kappa? And kappa is going to be the same in both cases because kappa is just looking at the number of correct classifications. So we can just double check to verify. So here is the kappa for the linear quadratic, and this should be for not linear quadratic, for linear discriminant analysis, and here's for quadratic, and that should say quadratic at the top, not linear. I will fix that as well. And then sensitivity and specificity, will they be the same? What do we think? No, they're going to be a little bit different because the distribution of errors was different. And so because these are specific to the types of errors. So here we see for linear, we get a sensitivity of 0.77, specificity 0.83. And again, I should be changing these titles to quadratic, and I'm forgetting to do that. I will fix that. So here's for quadratic, sensitivity and specificity become 0.76 and 0.84. And of course, we can do our receiver operating characteristic plot and look at the area under the curve. So here you see we actually get a slightly larger area under the curve for linear than we do for quadratic, but it's such a small difference, it's not particularly meaningful. This just has to do with how the classifications trade off for different thresholds. So it turns out that we get slightly better trade-off between sensitivity and specificity from the linear model, but that's probably random. It's probably, I wouldn't read anything into that. They're about the same.